Good morning, welcome to this next lecture on complex variables. We have started doing examples in contour integration and we have done a few. In the last class we were doing this particular problem, integral minus infinity to infinity sin ax over x dx. We have done this using a few methods and this is the last one, which I said is based on path deformation. Okay. So this I will write as integral minus infinity to infinity e to the power I a x minus e to the power of minus I a x over twice I x dx, okay. And this will be written as minus infinity to infinity on the real axis e to the power I a z minus e to the power minus I a z by twice I z. Once we stay on the real axis, all three are equal, okay. And here neither x equal to 0 is a singularity nor z equal to 0 is a singularity in the way we have formed it, okay. Now I was mentioning path deformation, I will repeat that. Our first theorem said three statements, and if any one was true, the others were true. So one of the statements was that integrals between 2 points are path independent. We integrate from z1 to z2, the integral is path independent, and that is equivalent to saying that integrals round closed contours are 0, okay. Integrals of f of z round closed contours are 0. Now we have theorems which say that if a function is analytic on and inside a curve, integral is 0, and we also have theorems which say if in a simply connected domain this following integral is 0, then f of z is analytic everywhere, okay. So now if f of z is analytic, in that region you will have integrals of closed contour being 0, and from the first theorem integrals between two fixed points being independent of path, okay. Now this function is such a function. Unless we go to infinities, this function is well behaved, okay. So we are going to consider that integral starting from minus infinity, we move along the real axis, there is no problem at z equal to 0, okay, and we should be moving straight away. But what I propose is that I will hold the edges fixed just as we do in this case z1 and z2, okay, and I consider the following path which comes from minus infinity, but around 0 it takes an epsilon radius path and again proceeds to infinity. I can do this. Why? Because the function is analytic in the region we are considering, okay. Why? Because that is equivalent to sin ax over x. Sin ax over x is a well behaved function, okay. So I consider that this integral, this particular integral will be same whether I come from minus infinity and go straight to infinity, or I take a slight detour around x equal to 0 with a radius epsilon. Okay. So, now I consider, now I break up, I will consider J1, which is this integral minus infinity to infinity, okay, e to the power of I a z by twice I z dz, okay, along this contour, along the contour I have found, okay. And then I will also consider J2, so we will have to make it C, okay, because it is not a straight line, we will make it C. Now I will also consider this integral minus infinity to infinity, now with a minus, okay, with a minus e to the power minus I a z over twice I z dz, again along the same contour. The sum of these two should equal this integral, that is the contention, okay. Why? Path can be deformed, okay. Now let us look at J1, okay. Now what I do with J1 is that I will continuously deform this path, I will continuously deform this path, and I can do so till I hit a singularity, okay, and I will finally make the path a circular arc of radius infinity in the upper half plane, okay. So this integral is now over CR e to the power of I a z by twice I z dz, okay, as limit r goes to infinity, okay. Now you can watch that the conditions of Jordan's lemma apply to this. Conditions of Jordan's lemma apply to this, okay. We have a function 1 over z which uniformly goes to 0 as the arc, circular arc, acquires the radius r infinity, and hence e to the power I a z, this 2I is just a constant, integral over that circular arc, okay, limit r tending to 0, infinity, dz must be equal to 0, and a is positive, So this part is 0, one part is 0, okay. Now the other part J2, okay, J2 has a negative sign in it, okay, J2 is with a negative sign, so let us keep it minus, I again consider this arc C e to the power of minus I a z by twice I z dz, okay, and I start with the same arc, I considered, or same path I considered, which is coming from minus infinity, taking a detour epsilon radius and moving forward to infinity, okay. Now if I start deforming this path in the upper half plane, okay, and I move towards infinity, okay, what happens is that this form does not suit the Jordan lemma. This form does not suit the Jordan lemma. Jordan lemma has e to the power plus I a z with a positive. If I have e to the power minus I a z and z is x plus I y, okay, then this I and minus I gives me a positive. So, I get e to the power of minus I a x plus a y, and if y goes to infinity, this function will blow up for a positive. So, it does not fit the Jordan lemma, and in fact in the upper half plane this will go to infinity, this goes to infinity. Okay. So, then what do we do? What we do is we deform the contour. So, that means I am deforming the contour till I hit a singularity, that is why the function went to infinity. So, remember that in deforming paths I cannot go and touch a singularity, till I touch a singularity I am allowed. So, the upward deformation of this path is not allowed. Okay. So, let us look at it now. We will take this path, starting path with an epsilon detour around the origin, okay, but now I deform downwards. Okay. Now I deform downwards, but remember when I deform this path downwards, okay, suppose I go like this, come back like this and join, I could go like this, come back like this and go off to infinity, the two endpoints being held. I cannot cross the 0 over here, that means my path cannot cross the 0 over here. Why? Because when I separate this integrand out from the total, okay, from the total when I separate it out, here z equal to 0 was not a problem, okay, it is a removable singularity, but here z0 z equal to 0 is a pole, is an isolated pole. For this individual part, okay, the J2 part, z equal to 0 is an isolated pole. So, if I deform this path downward, I cannot cross it, okay, those are rules of path deformation. So, now what do? I deform, I take this to infinity, from infinity I come down straight, I go around the origin, go back up straight to infinity and then close this. This is my CR in the lower half plane. Okay. Now again on CR Jordan's lemma is applicable. Jordan's lemma is applicable. Okay. For A being positive, the downward negative half plane is applicable. Okay. So, the integral on this part goes to 0. This integral that we are doing in the deformed path that has gone into the lower half of the complex plane, the CR part is 0 and the function is well behaved everywhere. So, this path, so this was the path I was taking. So, now this is the path I am taking, I go down here, go round the pole, come back up here and go to infinity, keeping these endpoints fixed. Now CR is 0, the function is well behaved everywhere except at x equal to 0. So, this upward integral and downward integral are in the region where the function is well behaved and analytic. So, this also goes to 0. So, this integral J2, okay, let us say it will still keep the minus over this contour e to the power minus I a z by twice I z dz. Okay. The minus portion will include later. Okay. This becomes equal to now So what is left in this integral? The integral is just going around the singularity at z equal to 0. That is all that is left. So that is equal to twice pi I times the residue. Residue is 1 by twice I, okay, and we are going in the counterclockwise direction. So that is, this part is okay, okay, but there is a minus in front. Sorry, this is clockwise. My mistake. This is clockwise. Okay, this clockwise and anti-clockwise does get confusing. So this is clockwise. So we are going down the pole in the clockwise direction. Okay, 1, 2, 3, 4. So the residue first of all is negative. First of all, the residue is negative. Okay, then there is this negative sign in front, so that makes it positive. So I get pi over here. I get a pi over here. Okay. So now what? The first part gave me 0, this part gives me 0, and this part gives me a pi. So that finally my integral minus infinity to infinity sine ax over x dx is equal to pi as before. So we have done this problem, a very standard problem in textbook, using 4 different methods or in 4 different ways. Okay. So now we will continue, we will take up a next problem. Next problem, I have lost count, let us call it the 5th problem or maybe the 4th problem. It is this: I have a real valued integral I is equal to integral 0 to infinity x dx over x cube plus 1. Okay. So we are going to apply contour integration to this. Okay. So as before, we replace this with j and an integral over a closed contour taken in the positive sense. We will call that c. Replace x with z. I have z dz over z cube plus 1. Okay. Now let us first look at the singularities of this function, poles of this function. So I have z cube plus 1 is equal to 0, or z cube is equal to minus 1, which we write as e to the power I pi plus I twice pi k. Okay. So that now my z ends up looking like e to the power I pi by 3 plus I twice pi by 3 k going from 0, 1, 2. Okay. So this gives me what? For k0 I get e to the power of I pi by 3. There is a pole there. Okay. For k equal to 1 I get e to the power I pi, and the next one is e to the power I 5 pi by 3. Okay. So this is actually 60 degrees, this is 180 degrees, and this is 300 degrees if you want to look at it in terms of degrees. Okay. So let us see that. So I have this complex plane and I have a pole at 60 degrees, I have a pole at 120 degrees, and I have a pole S at, let us say, 300 degrees. okay, 120 degrees apart I have poles. Okay. So now I have this integral that has to be done from 0 to infinity. Okay, I have to move from 0 to infinity, that is a must. Those are the limits here I have. So what is the contour I choose? I choose the following contour. Okay, I move from 0 to infinity. Okay, then I take a circular arc. We will consider this to be circular. I come up till a certain point, okay, at infinity, and come down to the origin. So the direction is this. Okay. So the closed contour includes one pole, which is e to the power I pi by 3. So let us see now j. So there are 3 portions, there is one portion, there is second portion, there is third portion. Okay. So j is equal to integral counterclockwise over path c z dz over z cube plus 1, which is now equal to the portion I want. Integral, I will write it straight away, 0 to infinity x dx by x cube plus 1, basically I, plus an integral over a circular arc CR with limit r going to infinity. Okay. Let me say z dz by z cube plus 1, and then an integral along a straight line. Okay. Let me say some c1 along c1, which is actually a straight line from infinity, z dz by z cube plus 1, and we are including one pole, so there will be a residue coming twice pi I times the residue at e to the power of I pi by 3. Okay. Now straight away, by using the degree of polynomials theorem, I have a numerator polynomial of degree 1, denominator of 3, there is at least a difference of degree 2. Okay. So this goes to 0 as r tends to infinity, this goes to 0. I am left with 2 pieces. So one piece is my I, let me call it I, the other piece is along some arc which is a straight line, z dz over z cube plus 1. Okay. That is equal to the residue. Okay. Now let us look at this particular term. Let us look at this term. So we are going to come down a straight line. Okay. So let z along that straight line, okay, be some r e to the power of I theta. Because it is a straight line now, theta is fixed. Theta is fixed. Okay. Then dz is equal to, here theta is fixed, so it is dr e to the power of I theta. Okay. When z is equal to 0, r is equal to 0, and when z is equal to infinity, r is equal to infinity. Okay. So now if we put it in terms of r and theta, my integral, this integral is given by integral z is r e to the power of I theta, dz is dr e to the power of I theta divided by z cube, which is r cube e to the power of 3I theta plus 1. Okay. Now here is a clever choice of theta. Okay. There is freedom in theta. I want to include only one pole. So there is this choice of theta I have. Okay. I could come this way, I could come that way. So here is a choice of theta. If I choose theta is equal to twice pi by 3. Okay, 120 degrees if I choose. Look at what happens here. This ends up, okay, more important, the limits. I am coming from z equal to infinity, z equal to 0. So I am going to come r equal to infinity to r equal to 0. Okay. So let us look at theta equal to twice pi by 3, and at the same time I will switch the limit. So I have minus integral 0 to infinity, I have r dr e to the power of I 4 pi by 3 divided by r cube e to the power 3I theta e to the power 3I theta twice pi by 3, which is e to the power I twice pi, which is 1 plus 1. So how does this look? This looks like minus integral 0 to infinity r dr by r cube plus 1 into e to the power of I 4 pi by 3. So you see, this part is my I, this part is my I, this part is my I, x dx by x cube plus 1 0 to infinity is my I, r dr by r cube plus 1 0 to infinity, r is just the dummy shift. Okay. So this is I. So let us see what happens. So this ends up looking like minus I e to the power of I 4 pi by 3. Okay. But I have I in front. Okay. So I have the total equal to I into 1 minus e to the power of I 4 pi by 3. That is the left hand side. Okay. So we need to compute the residue now. The right hand side is residue twice pi I times residue at e to the power of I pi by 3. Okay. So we will do that in the next class. Time is running out. So we will do that in the next class. We will start with this. Okay. Thank you.